We have been discussing atomic states in helium atom. The state functions have the form a space part times a spin part, and the spin functions we have obtained as follows: alpha times alpha, alpha times beta plus beta times alpha. A third spin function is beta times beta. And it is also alpha times beta minus beta times alpha. These spin functions have the property their ms values are 1, 0, minus 1, and this is 0 here. They are eigenfunctions of the permutation operator P12 with eigenvalue P. These all are symmetric with respect to spin exchange, these three functions, whereas the last function here is anti-symmetric with respect to spin exchange. Finally, they are eigenfunctions of S square with S value 1 for the three functions, whereas it is 0 for the last function. All right. Now we are going to consider the space part. Because of the Pauli exclusion principle, which requires that the total function must be anti-symmetric when the labels of the electrons are exchanged. And we have discussed that if the spin part is symmetric, then the space part must be antisymmetric so that the total function will be antisymmetric. Similarly, when the spin part is antisymmetric, as in the singlet case, then the space part must be symmetric with respect to electron exchange. So we can write for S equals 0, psi spin is an antisymmetric psi space must be symmetric. In electron exchange. It means that for S equals 0, this function, which we may write as singlet psi space, must have this property. If you exchange the electron labels, 2 with 1, the function values must be same. So, any function of 2 electrons of this type, when you use it in this expression, the spin part is this factor here. This is the antisymmetric spin function, 2 electron spin function. Now, on the other hand, for S equals 1, in this case, psi spin is symmetric, and any one of these 3 spin functions may be used. These are all symmetric. The space part, psi space, must be antisymmetric. In other words, the triplet, the space function for the triplet states must change sign when the 2 electrons are exchanged. Please remember once again that by space we mean only the space variables for the 2 electrons in this expression. Shortly, I'm going to show you that the energy values are determined entirely by the space part, either this triplet space, psi space, or singlet psi space. In other words, the energy of the state depends only on the S value. It doesn't depend on MS value. So whether it is this spin factor or that spin factor or that spin factor, for the triplet state, we always obtain just one energy, which means there is a degeneracy in the triplet states, and the number of degeneracy is equal to the number of different spin functions, which you may also count from MS values. All right. Next, we are going to discuss how to design suitable expressions for either singlet space functions or triplet spin functions. Now, the starting point for this purpose is the orbital approximation. Now, let us write the full Hamiltonian for the helium atom. It is equal to let me write this. Here, H is minus 1/2 del square minus 2 over R. A 1 electron Hamiltonian. Now, H1 means you will attach label 1 for the first electron to kinetic energy part, and also this R part, so this will become R1. H2 means the same expression, except that label now is 2. Here you will put 2, and that one is also 2. And 1 over R12 is the electron-electron repulsion. In other words, the interaction, the Coulomb interaction between the two electrons. Now, if we omit the interaction terms, then we obtain another Hamiltonian, which we call core Hamiltonian. It is just this part. Now, if you look at, or if you examine the physical meaning of this expression, you see that there are 2 electrons. And these 2 electrons are non-interacting because we have omitted the interaction term here. So each electron is independently moving with respect to the other one. What kind of motion is each electron doing? You see it from this expression. This is the Hamiltonian for a single electron moving in the field of a nucleus, and this nucleus has charge plus 2. All right? So it's a hydrogen-like atom. And we have discussed this problem before. So each electron H has eigenvalues. The one electron Hamiltonian has eigenvalues, which are En, and it is this in Hartrees. The corresponding orbitals are 1s, 2s, 2p1, 2p0, 2p minus 1, etc. These are the orbitals which correspond to these one electron energies here. Now, please note that the only difference between the 2 electrons is their labels. One of the electrons we call electron number 1, the other we call electron number 2. Each electron will have energies which correspond to one of these numbers from this formula. And their orbitals are the same except for label. For example, when we write such an expression, this means for the first electron, we have selected the 1s orbital. So remember, this is a function. In the function, we attach number 1 as the index label for the variables of the first electron. On the other hand, if we write 2 inside parentheses, that means we have selected a 1s orbital for the second electron. So that now in the actual expression for this, you attach the integer 2 as subscript to all the variables in the expression. The eigenvalues of this core Hamiltonian are simply written down because the two electrons in the core Hamiltonian are non-interacting. And we know that whenever the particles are non-interacting, the total energy is a sum, and the total state function is a product. So in this expression, this is the Schrödinger equation for the core Hamiltonian. Now, we may directly write the core energies are additive. It is energy of electron 1 plus energy of electron 2, or explicitly, this is minus 2 over n1 square using this expression. And this is minus 2 over n2 squared. And the two electron state function for psi core is simply a product. So we may write it as psi n1 L1 M1 times n2 L2 M2. The first factor is the space function for the first electron, and the second one is the corresponding space function for the second electron. This is an orbital product. Such an orbital product is always an eigenfunction of z component of total angular momentum. What is Lz? This is the z component of the total orbital angular momentum. And such orbital products are always eigenfunctions of this operator. So we may write Lz psi core equals psi core times ml. So the eigenvalue is m sub l. And if you apply the definition of Lz operator in terms of L1z and L2z and use this expression, because each factor separately is an eigenfunction of either L1z or L2z, then we will obtain in here for the total ml, it is the sum of m1 plus m2. In other words, the total ml is obtained by adding the small m values for each orbital in the product. Now, in general, what we have written down here for the orbital product is for just two electrons. But we can generalize this to more than 2 electrons. So atoms, those atoms with 3 electrons, 4 electrons, 5, and so on. The procedure is quite similar. For the space part, we multiply the orbitals. The number of orbitals to be multiplied is equal to the number of electrons in the atom. Any such orbital product which contains more than 2 orbitals will also be eigenfunctions of Lz. Of course, Lz in that case will have more terms for the 3rd electron, 4th electron, 5th electron, and so on. But nevertheless, such products are eigenfunctions of Lz with the ml value given by a sum of the small m values of the orbitals which are present in the product. So in general, we can write this. ml is sum of small ml values for each orbital in the product. For example, 1s times 2p1 times 3d2. For the first electron, we have picked 1s orbital. For the second electron, we have picked 2p1 orbital. And for the third one, 3d2. These are just space parts. The total ml, or let us write small ml values. For the first factor, what is the ml value of the s orbital? 0. For this one, ml value is 1. And for the third factor, it is 2, this factor. Now, the product function is an eigenfunction of Lz, and the ml value is 0 plus 1 plus 2 equals 3. You just add up the small ml value of each orbital in the product to obtain the total ml. Please note once again that we are using capital letters for m to denote the total. On the other hand, for single electrons, we are using lowercase m values. Okay, let us now show, or let us return to helium atom, just 2 electrons. And shall I write? Okay. So, the space part of the state function is taken as an orbital product, and the spin part in this expression is one of these 3 spin functions for the triplet state, and this spin function for the singlet space. Let us simplify the energy expression of, according to variational principle, we calculate the energy in this manner. This H is the exact H, including the 1 over R12 term. Psi trial has psi space. So let us include the complex conic also, times psi spin, H in between, psi space, times psi spin. Here the integration is over space variables and also over spin variables. Now, in other words, in this problem, there are 2 electrons. Each electron has 4 variables. 2 times 4 is 8. So this is a 8-fold integral. There are 8 integrations. 2 of the integrations are over spin variables because an electron has just 1 spin variable. There are 2 electrons here, so the total number of spin variables is 2. The remaining 3 plus 3, 6 variables are space variables. Because this Hamiltonian doesn't contain spin variables, this integral is factorized as product of 2 integrals, 2 independent integrals. And we can write this as integral over space variables times integral over spin variables. Integral over space variables is psi space times or in between Hamiltonian psi space d tau space, whereas the spin variables spin integral is the spin part here, psi spin times this psi spin, and the integration variables are spin. Notice that this is just normalization integral for the spin part. And in fact, the normalization integral for this spin function is just 1 over square root of 2, and this one also 1 over square root of 2. These are already normalized, alpha times alpha and beta times beta, so that when we include such factors, in the case of ms equals 0 or of triplet or and singlet states, then the integral here is simply 1. So that the energy is determined entirely by the space part of the total wave function. And this result shows you that energy is the same, whether we use for the triplet state, whether we use this spin function in the product or that one, as long as the space part is the same. So here we have shown explicitly that the energy does not depend on ms value. We have the same energy for ms equals 1 or 0 or minus 1, because the energy, they all have the same space function, and the energy is determined by space function. On the other hand, the value of this integral over space variables does depend on whether you use a singlet psi space function or triplet psi space function, because remember, for the triplet state, the spin part is symmetric. Therefore, the space function must be antisymmetric function with respect to electron exchange. On the other hand, for the singlet state, because the spin function is antisymmetric, the space function must be symmetric. So that integral is calculated with different expressions for psi space, depending on whether we are talking about a singlet spin state or a triplet spin state, which means we are going to obtain different results depending on whether it is s equals 0 or s equals 1. In other words, energy does depend on s value. You have different energies for different s values, but energy is independent of either ms or ml. Now, let's go more explicit, and let us consider the ground state of helium atom. We are going to select orbitals for the ground state from this set. Now, ground state means that we are interested in the lowest energy of helium, which means in our selection of the orbitals for the two electrons, to get the lowest energy, we select the lowest energy orbitals in our product. We select 1s orbital for the first electron, and for the second electron also we select 1s orbital, so that this is our product. Remember, psi core times, we are using this expression. Orbital for the first electron times orbital for the second electron. Now, to obtain the lowest total energy, we select the lowest energy orbitals for the first electron and also for the second electron. So this is obtained from this expression here. Notice that this product is symmetric with respect to electron exchange. If you exchange 1 with 2, the expression stays the same, isn't it? So this is, we may write, because this is symmetric, then look at this expression. If this is symmetric, the spin part has to be antisymmetric. Which one is the antisymmetric spin function? This one. And this spin function has s equals 0, or in terms of spin multiplicity, 2 times s plus 1. Spin multiplicity is 1. In other words, it's a singlet. This orbital product cannot be combined with one of these triplet spin functions. Why not? Combination means multiplication with the, or this expression, psi space times psi spin, all right? We say psi space is combined with psi spin in the sense that they are multiplied. Because this space function of two electrons is symmetric with respect to electron exchange. And the triplet spin functions are also symmetric with respect to spin exchange. They cannot be combined because it violates the Pauli exclusion principle. Pauli exclusion principle is stating that when all four variables of the electrons are exchanged, the state function, the full function, must change sign. The full function must be antisymmetric. Therefore, such a function of such an orbital product is symmetric with respect to electron exchange. It can only be combined with an antisymmetric spin function. Hence, only a singlet state is possible from such a selection of orbitals. Now, this function, therefore, corresponds to S equals 0 in the sense that when you use it in this expression, you can multiply it with the singlet spin function only. Also, ML value for such a product is, as we have shown it before, in a product, we just add the small ML values of each orbital in the product. What is ML value for S orbital? 0. This is also S orbital, so 0 plus 0 gives 0. This means that the L value for this product you start from knowledge of ML to conclude what should be L value. You know that for a given L, what are the possibilities for ML? All numbers between plus L and minus L. So here, we know that there is just one ML, which is 0, and therefore we conclude that L should be 0. Now the term symbol for the ground level is L is 0. What is the letter code for 0? It is S. Remember, term symbol is, you write multiplicity as a left superscript, and then L value, but in terms of the letter code. So here, corresponding letter code for L equals 0 is S. This is capital S. I have repeated this many times. Whenever we write symbols for more than one electron, two or more, we use capital letters. On the other hand, for a single electron, just one electron, we use letters in lowercase. And the multiplicity, spin multiplicities, 2 times 0 plus 1 is 1. So this is singlet S, the term symbol for the ground state of helium atom. Now there is a notation, convenient notation, which indicates which orbitals are used in this product. For example, here, for both orbitals, we have taken the same orbital. We show this selection of orbitals in the product by such a notation. 1s2. 1s2 means 1s for the first electron and 1s for the second electron in a product. 1s times 1s, what you see over there. But this is just a short notation which is indicating which orbitals have been selected in the product, such as this one. This notation is called electron configuration. Electron configuration of course this is for the ground electronic state, for the ground electronic state of helium atom, but the main term is electron configuration. Now, let me give you an example about how this is used. The 1s orbital in the hydrogen atom, 1s orbital is a 1 over square root of pi times e to the minus 2r. Here we have, there is a factor 2 over 3 over 2. This is 1s orbital, 1s hydrogen-like orbital with Z equals 2. Now, in the variational procedure, replace 2 with a variational parameter, with a parameter zeta, to write 1s orbital s The idea here is that the function changes when you select different values for zeta. If zeta is 2, it is this expression, all right? But if you select some other value for zeta, then this function is going to change. As a result, in the variational expression, psi trial, psi space, Hamiltonian psi space, d tau space, the value of this integral depends on which number you use for zeta. Okay? The variational principle guarantees that whatever function we use for in this integral, we cannot go below the exact minimum. We have discussed this when we introduced the variational principle. Therefore, whatever value for zeta we select in this expression, it is not possible to obtain a value for this energy from this integral, which is lower than the exact ground state energy. Therefore, we say, or we proceed like this. We substitute this expression into the this integral with initially an unknown value for zeta, but zeta we know is just a constant, it is just a parameter. Obtain this expression in terms of zeta, and then choose zeta which will produce the lowest possible value for each trial. So when we do that, in other words, now we write for this expression 1s1 times 1s2. Explicitly, it is this expression. This is the first fact, e to the z minus zeta r1. I have attached electron label for the first electron using this expression. Just put r1 times the second one. I have put r2. We are using spherical polar variables here. Then this expression is substituted into this integral. Integration is done. And the result of integration is this. Zeta squared minus 27 over 8 zeta. If we had used 2 for zeta, then this expression would give you 4 minus 27 over 4. If we had used this zeta. But we want to select zeta. The name of this symbol is zeta. So that this number is a minimum. What is a mathematical criterion to obtain minima or maxima? You take the first derivative and set it equal to 0. Here, what is the variable for the minimum problem? Zeta. So we take the first derivative with respect to zeta and set it equal to 0 to get the best value for zeta. All right, our time is almost up, but first derivative with respect to zeta and set it equal to 0. And you see that it is 2 times zeta minus 27 over 8 equals 0 after taking derivative. So that best value for zeta is minus 27 over 16. Or this is, plus zeta, 1.688. So if we take zeta as 1.688, then the value you will obtain here will be lowest possible value among all choices of zeta. For example, it means that here zeta is 2. If you use z equals 2 or zeta equals 2, the value here will be larger than the value when you use z equals 1.688. This value is going to give the lowest value. And we know that this lowest value cannot be lower than the exact ground state energy. Therefore, with this functional form, this is the best value for zeta.